What I just showed you earlier was an equation for calculating how a population that has discrete generations grows over time. Now let's take the example of a population that has continuously developing generations. So you can't really tell where one generation ends and where the next begins. There's a group of individuals that is constantly producing new individuals. In this case here, rather than modeling how the number of individuals changes, we're going to model the rate of that change. Oh my goodness, there's a dn dt, so you're probably in freakout mode at this point, but don't worry about it. It's actually not that complicated. So what we're going to do is we're going to model the rate of change as the number of new individuals that are born, B, minus the number of individuals that die, total. So the number of individuals that will change in that population is just the difference between the two of those. Now, if we know something about the population size and the rate at which individuals are born at, on average per individual, then we can substitute the total number of individuals that are born by the population size and the average birth rate per individual. And we can do the same for the death rate. How many individuals are there? What is the rate of their death on average per individual? And that is how many new or fewer individuals we're going to have in the as time goes on. Now again, this is continuous, so it's instantaneous. When you put these two numbers together, dn dt now is, we're just going to substitute these in, is going to be b times n. Okay, I've just switched the b and the n, the little b and the n just for kicks. And little d times little n is how many individuals, or what the rate of death is in that population. We can group like terms together, and that b minus d is what we refer to as the intrinsic rate of increase. So this is the population growth rate of this population. So if you take this little r and you multiply it by the population size, you could figure out what the rate of growth of this population is. So the rate of growth, dn dt, is equal to little r times n. We can calculate actually, or we can express little r as the per capita rate of change. So if we divide both sides by n, what you can see here is that the little r is the rate of change, the dn dt, divided by n, which means per head, per capita. So that's another interpretation of what little r means. It's the per capita rate of increase. The continuous form of this population equation, the dn dt equals rn, has the property that if r is positive, the population is going to be increasing. If r is negative, the population is going to decline. And if r is 0, then the population will stay constant. So if you map abundance, the population size or the population density as a function of time, t, for our equation, dn dt, the rate of change of the population is equal to rn. If the abundance is greater than 0 and r is greater than 0, then what you get is a population that is going to be increasing. So when does the population actually sit still? Well, it sits still when the initial population size is 0. That's kind of stupid. If you have no population, it's not going to grow. And when the rate of increase, r, is also equal to 0. And that actually is kind of an interesting situation. So these are the two instances where population growth rate is not going to change. So here's an example of n is greater than 0 and r is greater than 0. And this is what the population would do. This is often what we refer to as an exponential growth model. And one of the features of this very simple equation is that there's basically no limitation on how big a population can grow. If r is greater than 0, this population is going to go to infinity. In fact, it's exponential growth. And the flip side, if R is negative, this population is going to go extinct. It's going to go to zero.